Hello! Welcome to the GummyBears Robotics FLL Tutorials program. My name is Adrita and I have 4 years of experience with FLL Challenge as part of the Unicorn Dreamers, an all-girls FLL Challenge team from Acton and Shrewsbury, Massachusetts. Today, we are going to continue our work with sensors, mainly focusing on the gyro, distance, and rotation sensors. Here is a quick overview of what we will be covering today. This is part 2 of Intro to Sensors. First, we will look at how each of these sensors work and how they can be used in your programs. Then, we'll go through real examples with code. Finally, we'll put everything into practice with the fun obstacle course challenge. The distance sensor uses sound waves to tell how far away something is. It can show you the distance in centimeters, inches, or as a percent. With the wait until block, you can make your robot do something, like stop, when it sees something closer than 15 inches. Instead of checking the distance is less than a certain value, you can also check if it's greater than or exactly equal to that value. This is great for missions where your robot needs to stop right in front of something, like a wall or a mission model. Using this sensor helps you avoid relying on only timing or guesswork. Here's how you might use the distance sensor in a program. First, you set your motors and choose a speed. Then, you make your robot keep moving forward. Meanwhile, the wait until block uses distance sensor A to constantly check the distance to whatever is in front of it. As soon as that distance is less than 15 centimeters, the robot stops its movement. This movement increases reliability when your robot is interacting with the field elements. Spike Prime also includes a built-in gyro sensor that measures your robot's rotation angles, such as yaw, pitch, and roll in degrees. This is especially useful for making precise turns and detecting changes in orientation. A common example is gyro sensor-based turning, where you can use the wait until block along with the green Boolean block and the light blue yaw angle reporter block to constantly check if the robot's yaw angle is approaching a target value. This setup lets your program continue only once the robot has turned far enough, making your turns more accurate and reliable. Also, resetting the gyro at the start gives you a clean reference point. Now, let's try a pivot turn using the gyro sensor. First, we set the motors and start a left turn with a steer value of 50%. This makes one wheel rotate while the other stays still, creating a pivot turn. To make the turn more accurate, we use a slow speed, just 10%. Then, we use the wait until angle block to monitor the robot's yaw angle. When the angle goes past 90 degrees, the robot stops. This helps prevent over or under turning. In the animation, you will see the robot slowly turn left to about 90 degrees, then stop. Please note, for left turns, the yaw angle decreases, so when using wait until block, your Boolean condition should check if the angle is less than negative 90 degrees, not greater, since the values go down as the robot turns left. In the second example, we try a spin turn to the right, where the wheels move in opposite directions compared to a pivot turn. A spin turn is a bit faster and works well in tight spaces. The code logic is similar. We monitor the yaw angle and stop the robot once it goes beyond 90 degrees. In both examples, you might have noticed that the robot didn't stop exactly at 90 degrees. If you double-click the robot dashboard, you can see the exact angle the robot turned. This difference is caused by gyro lag. The sensor reacts a bit slower than the robot's actual movement, so it detects angle change later than it happens. The robot's movement speed affects gyro lag a lot. If you try different speeds, you'll see that the faster the robot turns, the larger gyro lag becomes. That's why it's best to use a slow speed for accurate turns. Sometimes adding a small buffer value to your target angle also helps. We'll explore these techniques more in advanced navigation topics. The rotation sensor is integrated into the motors and tracks the amount of rotation. This allows us to measure how far the robot has traveled or how fast it's moving. What's great about this is that you can use the data to move the robot to a precise position, like instructing it to rotate exactly 720 degrees, or 2 full wheel rotations. It's especially useful for controlling accurate movement in a straight line. In the above example, we let the robot stop once motor C's position is greater than 360 degrees. We also use the rotation sensor to help spot when a motor gets stuck. If the motor is trying to move but can't because something is blocking it or it's too heavy, the sensor can tell us that the motor isn't turning like it should. This way, we can find out if there's something wrong. like too much friction or blockage. Now, it's time to put these sensors to the test. This challenge combines distance sensing, turning with gyro, and rotation-based control. The idea is to navigate an obstacle course with specific stopping points and turns. Make Lego walls as shown in the picture and have the robot navigate the path shown by the blue arrows. If you want to make the challenge more interesting, you can bring the walls closer together so that the robot will need to follow an accurate path to reach the finish line. You'll need to think about when and where to use each sensor for the best results. Who's ready to give it a try? Thanks for watching this video. Make sure you like and subscribe so you can be notified when we post the more advanced topics in FLL. If you have any question, feel free to leave a comment down below or reach us through our email at fllgummybears@gmail.com.